Hello everyone, nice to have you here again for this fourth, I cannot say, part of this series of webinars going through all our wavelengths like this. Today we are going to speak about the MWIR, mid-wave infrared, and I'm really glad again to be with you, and we're going to speak especially about our FX50. About myself, again, I'm still Mathieu Marion, working at Specim as a lead application specialist, and I'm happy to be with you with this journey like this over the full spectrum. The agenda today is the following one. We're going to speak quickly about the company, quick introduction about it. What is mid-wave infrared hyperspectral imaging? We're going to speak as well of some applications that really benefits from this spectral range, which is not that common, to be honest with you, but it's really like full of things, full of surprises. What can we offer for you? How you can use this camera? Which kind of accessories we have to use this camera? We're going to speak about illumination, because here it's something which is very different. We are talking about the thermal infrared, so you can forget about halogen, things like this. So we have like really dedicated illumination. And then I will be here after this presentation for you, waiting for answers, and I will do my best to answer, waiting for questions, sorry, and I will do my best to answer for your questions. About Specim. So, you know, Specim has been founded in 1995 and is a spin-off of VTT, which is the Finnish National Research Centers. Over those years, we have sold more than 10,000 hyperspectral devices, meaning like spectrograph, cameras, things like this. What about 90 people? And we grow annually about 20%, it depends on the year. And since 2020, we are part of Konica Minolta, which has been really useful to expand our business globally. And since we are talking about global presence, I would like to highlight that our headquarters is still in Oulu, and we have local presences in the United States, also in Europe for Oulu, but also in Barcelona, in Munich, and as well in China. And then we have a lot of distributors all around the world, which can, you know, like be contacted for getting information about our products. About MWIR spectral imaging, so basically it is still part of hyperspectral imaging, and you know, hyperspectral imaging is a combination of spectral and spatial information. So spectral information, basically you can depict the molecular structure of something, so you can get information about what is what, or what is the concentration of something. But then you have the spatial information, so that means that you can have an image, and then for each pixels you can get those spectral information. So you can see the distribution of something, you can see the size and the shaping of something. So this is basically the combination of both. This is what you can get with a hyperspectral camera. And now, if we speak about the spectral range, now we are using the mid-wave infrared, and the camera we are going to speak about, the FX50, which is actually just here. It is between, sorry, it's a bit heavy, just like this. It is like measuring spectra between 2.7 and 5.3 micrometers. So this is what we have. And as you can see, it is far away from the visible. It is very in the thermal infrared. It's not the long-wave infrared, which is coming soon, and actually I will come back to it at the end of this presentation. It's like in between. What are the benefits? The applications that benefit from that. So of course there is like a lot of potential for the recycling industry. So this is the only camera which can really separate plastics, but not only color ones, but also black ones. I will speak about it a bit later. It could be useful as well for geological and related applications like mining, for metal industry, and also for safety and security. Of course, there are other applications, but those are the ones I'm going to speak about in this presentation. About plastic sortings. Well, as you know, first of all, we have cameras dedicated to that. We have our FX camera, we have the FX10, we have the FX17. We also have the SVIR camera and the FX50. And here we have been measuring different types of plastics. The most common one, you can see the list, I'm not going through. And we have tested how those can be separated with different camera we have. But with the FX10, you have only a little bit of IR, so you can really measure some peaks between 800 and 1000 nanometers. So you can see something, but well, it's not really reliable. Not every plastic, they have something. They have some spectral features. With the FX17, it's already much more. It's between 900 and 1700 nanometers. Already from here, you can separate much more plastics if they are not black. This is a camera we sell the most for the recycling industry. Then we have the SWIR one, which is between 1000 and 2500 nanometers. You can sort like what the FX17 can do, maybe a little bit better, but well, okay. The price gap doesn't justify necessarily to use a SWIR. But then, here comes the FX50. With the FX50, you can sort plastics, all of those, if they are black, but also not black. And here, we made some feasibility studies on those materials, those plastic samples, when they are white, and as you can see, like here, all the camera can perform rather well, the FX50 as well, but when we are talking about black plastics, only the FX50 is suitable and can do. And here you have an example of PE, ABS, PS, PA, and PC. Well, the PC was transparent, it was not black, but still, it can be sorted. And in order to go further and to really show you it is true, we have here measure all of those, and here you can see the spectra. And you can see the spectra is not flat at all. It is full of spectral features, and those plastics can therefore be sorted from each other. Regardless, by the way, the coloration, the spectra will be the same if it is a brown, white, blue, or black plastic. The spectra will be exactly the same. So here you can see this camera is very suitable to sort all those type of polymers. Another type of industry which could benefit for the mid-wave infrared and the FX50, this is the metal industry. The FX50 is very suitable to detect different types of contaminants and impurity, like oil, oxides, but some other ones that you can find organic residues on the metal stack. And I will come back to it just in the next slide. So if you need to optimize and to control your process, your production process, this is really the camera for it. It can also monitor temperature, because if you use the camera and then you can convert the raw data into radiance, you can then fit a Planck emission curve of a black body, and then you can really estimate what is the temperature that you can have on your samples. And this camera is very suitable for samples between 50 and 1000 degrees Celsius. So if I come back to the detection of different types of contaminant, this camera can do really well, and I would say even more than traditional IR camera can do. Here we made a test. We took a metal sheet like this and a piece of fabric as well. And on it, I spread 3 different types of oil. I measure those then with the SWIR camera and then with the FX50 camera. And as you can see, the sorting, the detectability is actually much better with the FX50 than with traditional IR camera, which can cover the spectral range between 1000 2500 nanometers. So this camera is very, very reactive actually to oil. So that means that this type of contaminant can be nicely detected. Be aware that this contamination by oil could not be seen with the eyes because the oil was transparent. Another type of application where it could be really useful to detect contaminant, it is for glue. You know, gluing is very important. And the quantity you apply is also very important and need to be monitored. If you put too much, you waste money. If you put too little, basically it doesn't glue enough. So the monitoring, the distribution, but also the quantity is important. And here again, we bought 3 types of glues and we applied it on a rubber and also on a cardboard. We applied it and we tried to detect it with FX17, SWIR camera, and also the FX50. And here again, you can see FX17 can detect pretty well, but not perfectly well. For example, if you look at the rubber top left, the FX17 cannot see anything. The SWIR can start to have a hint of it, but the FX50 can really depict really, really well where it is spread. So again here, this camera could be really useful for process optimization like this. Another type of application where the MWIR would be really beneficial, it is for geology and also the mining industry. I must say that this type of wavelength, this type of camera covering these wavelengths is not the most common one. So that means that there has been only little research done. But from what we have seen, it seems that this camera is very, very useful to separate different type of hydroxide-bearing silicate, carbonate, and also quartz. So when you want to make research about it, here this camera will be the right one. You can measure different type of cores, and here come what we have. We call that the CISO rock. The CISO rock, it is our platform where we will put more than one camera at a time, and the FX50 could be integrated in there. The CISO rock is very suitable to put a large box full of drill core, and the FX50 could provide data which could be very valuable to separate and to identify different type of minerals. Another type of application where it is very useful is for defense and security. You can imagine that camouflage material, typically it is made to mimic what you have around you. So we have all seen like nets, as you can see here. So it is green, it could be you know, like sandy, a bit in color, so that you can have something underneath to be hidden. It is hidden visually, but not necessarily, you know, in the long-wave infrared. So for instance, with the IR, you can depict the material, but with the mid-wave infrared, you can depict the material even more accurately in a way, because most of the materials, they have been investigated visibly up to 2,500 nanometers, but very rarely up to 5 micrometers. So here this camera could be very useful. It is also very useful if you want to make some gas detection. So you can imagine you have a rocket, you have some ignition gas, an ignition process, and you want to monitor like it is well optimized or not, which kind of gas is burning where and when. Here this camera could be used for that. And also for material science when you want to separate different type of materials. So, talking about the application is nice. Now I will talk to you about what we can offer for you. So again, I will show it to you because we are proud about it. We have here the FX50. As you can see, whoop, this side is actually better. Here you can see the lens. Here we have all seen it. I can put it back. So the FX50, which is between 2.7 and 5.3 nanometers, it has 640 spatial pixels. So remember, it's a line scan device. So each pixel having independent spectral information. The frame rate could be pretty high. It is 377 frames per second, looking at the full spectral range. If you want to reduce it, if you reduce the spectral range, that means the camera can be even faster. And if you think about black plastic, for instance, the typical region which is useful is between 3.3 and 4. It depends on the plastic you want to sort, but typically it's about that, 4 micrometers. The camera can be then much faster because you don't need to read everything. The dynamic range is high. It is a MCT detector. Well, you can see everything here. I don't need to go through each of the parameters. It could be used in the laboratory. So we have a scanner dedicated for it. It is a 100 by 50 scanner, so you can put samples as large as 100 by 50 centimeters. It's compatible with our software, Lumo Scanner. Here you can acquire data. Be aware that we have 3 lenses available with this camera. We have 24, 45, and 60 degrees. So depending on the samples and what you want to measure, you can make a very good measurement with high spatial resolution. You can see even like wide field of view. Here you can see our MWIR setup. It consists basically on the FX50, which is here, mounted on our B scanner, the 100 by 50 scanner, with its illumination. 100 by 50 scanner, you are used to this name already. It is suitable for samples as large as 100 by 50 centimeters. Here you can see the FX50, which is measuring spectra between 2.7 and 5.3 micrometers. And you can see it is fully cased. The lens is also part of the casing. Why is that? Because we are actually really part of the thermal infrared. And as I was explaining before with the SVIR webinars that you have seen already some weeks ago, it is important to control the temperature of the spectrograph, but also of the front objective, because if the temperature change, its emission would change as well. So in order to keep a radiometric behavior constant of the camera over the time, you need like this to stabilize the full optical part. So here it is. Then here we have the illumination, which consists of two radiators. Another thing which is actually quite important and different from what you have seen before, it is the white reference. Between 400 and 2500 nanometers, the white reference you have seen was made out of Teflon. This time it's made of aluminum and it is sandblasted to make it more diffuse. So here you have the full system, as I explained, and we are going to measure a box full of geological core. And to measure that, there will be a movement, as you know, and I can use the system using our software Lumo Scanner. To do so, we just need to activate it. Then we have the samples moving underneath the camera, and because it's a line scan device, then frame after frame, it can reconstruct the hyperspectral cube. Another thing which is important is not to heat up your samples. A common mistake with these spectral regions is actually to heat up the samples. You don't want to do that because then they will start to emit at the same wavelengths where they absorb. So it means the spectral feature will vanish. So keep your samples and the white reference at room temperature, ambient temperature, and just measure like you will do normally. This camera could also be used on the field. Like as you can see here, we have the rotary scanner 50. So the camera is looking sideways, like I'm doing, and then by rotating, you can just acquire like this a hyperspectral cube of a thin, which is outside. So this camera could be used for this purpose as well. Be aware that when you use it like this on the field, you need to have the radiometric calibration, and here we recommend to use a black body for that. There is the Sisu rock that I was explaining for geological applications, so where you can monitor actually drill core in a box. And here the cameras, the FX50, could be mounted in the cabinet, and in the cabinet you can have up to 3 cameras, but actually we have an extended version where up to 5 cameras could be mounted. So here it is. Then we have the software, as I was explaining. This is compatible with our Lumo suite, which is actually relevant for you if you're an integrator as well, because it means that this camera is compatible with our software development kit, where you can actually just put the camera like this in your industrial environment. At the top of your conveyor belt, you can communicate with the camera and create your own environment. Another thing which is important, it is the thermal illumination that I wanted to speak about it. We have it. We have a thermal illumination designed and made for this camera. So basically, you see it consists of 2 radiators with heating element inside, which looks like electrical barbecue basically, and they emit because they follow, you know, like the Planck emission curve, and they are emitting at about 900 Kelvin, 650 degrees Celsius. So you can see here they really emit nicely between 2.7 and 5.3 micrometers. So that's why actually we choose this temperature. So this is our thermal illumination. That's the one we use, and that's the one you need. Here you cannot use the solar illumination. This is not applicable because, as you can see, or it's not that it's not applicable, but you have a lot of atmospheric absorption or contribution. And you see it really strongly on this graph at the top here. You can see that between 2.7 and 5.3, you don't have so much sunlight, which is actually reaching the Earth because of the atmosphere. And you see it very well when you measure the camera as well in the lab, because at the middle of the spectral range, at about 4.3 micrometer, 4.2, 4.3 micrometers, you really see a dip in the white reference signal. It works well, it's normal. The sensitivity of the camera will be continuous, but it's just that there is no light which is passing through the air because of the CO2 which is there. By the way, this dip is very useful because you can check if your camera is nicely spectrally calibrated. Why hyperspectral imaging? I think you know already about it. It's non-invasive, non-destructive. It can replace manual and visual inspection with like this with cameras. time-consuming lab test in a way that now you have an image, so you don't have to make, for example, like point measurement. You directly have an image like this. Real-time inspection. So here again, you can use the camera in real time, like for like process monitoring, sorting, things like this. You can cover 100% of the product stream. You don't need to take necessarily something out of your stream to measure it and then to do what we call at-line. You can really do the things online. Improve chemical grading, and in a way that here you can really make qualitative but also quantitative analysis, close to 100% accuracy. Detect a range of characteristics simultaneously. It means that you can look at different parameters all at once, and you have a limitless amount of application where you want to play with. Okay, so now we'll be ready for the Q&A. Be aware that if you want to contact us, we can measure sample, we can arrange demo, you can ask for a quote. Contact us at info@specim.com. Be aware that after this webinar, there will still be another one, the 22nd of February, and this time is going to be about the long-wave infrared. Thank you very much. So now I'm here, happy to answer your questions, and I see that we started to have some already. So I will go through one by one, I will read them, and I will do my best to answer. If I cannot, we will come back to you later. I cannot say I know everything, it's impossible, but I will do my best. So can you teach in a new polymer material you want to detect by your own, or is it only possible by Specim? Well, I would say it depends on the software you are using. But in any way, Specim is not going to teach a new polymer. So if you use your own software for the data processing, so basically you can make your software in such a way that you can add time after time a new polymer to be sorted. If you want to use our insight, you have the possibility to teach a new polymer in a sequential approach. So yes, you can add new polymers. So if, for example, first you want to sort some PE from PP, and then you want to add the ABS or like the POM or whatever, you have the possibility then to add it. Be aware that in this presentation, we did not speak that much about the Specim one. It's because, in fact, at the date of today, the camera that we are having, the FX50 that we just released like a few weeks ago, is not compatible yet with Specim one. But in about July, it's going to be compatible, and then you will have the possibility to do that with Insight. Could this be used to analyze content of used paper machine felts? Well, I have to say, I had to check what was like a paper felt on internet when I saw the question coming. I understand that those machines are used to remove basically water content or some moisture from the paper manufacturing process. I have to say, if you want to monitor like water content and things like this, maybe the FX50 is not the best device for that. I would prefer to use the FX17, for instance, and also the SWIR camera. But FX17 can already give you some good hint about water content. Actually, can give you some pretty accurate measure about it. So I would prefer to use that. But if it is to analyze the content of used paper, here it needs to check if it has any special spectral signature to separate the used one from the new one. But just like this, I have doubt. How ruggedized the FX50 for field application? What you saw part of the presentation, you could put the FX50 on a tripod, and then it can be on a rotary scanner, and then you can use it outside to rotate like this to acquire an image on the field. So it could be used for that. Having said that, you have to be careful that if it's raining, the camera is not ruggedized to have some moisture getting in there. You saw it has some fan for ventilation purpose. And anyway, if it's raining, it means that there are clouds. If there are clouds, it might be that you don't have that much of the signal which is coming. Another thing is like you have to use it as well within the usable temperature range. It's between +5 and +40 degrees. So if it is too hot or too cold, you cannot use it. But be aware that you need to have a black body as well part of your field of view of the image that you are taking so that you can actually perform the radiometric calibration. Has this camera been tested for dry, hot, desert or wet, hot tropics? Well, as I say, so if it is too wet, the issue you can have is like actually it's going inside the camera. You see it has some opening. Too hot, it needs to be below 40 degrees. So we did not test it like this in desert, neither tropics, but keep that in mind. One of the applications mentioned was the analysis of rocket plumes, exhaust gases, yes. What is the maximum temperature of the target? Can it observe temperature up to 2000 degrees Celsius? You have to think about emission of a black body curve. So basically now you have a camera which is looking between 2.7 and 5.3 micrometers. If you put a gas or whatever, an object, something which is at a certain temperature, it will emit not exactly following the Planck's law of the emission of a black body, because it will have its own emissivity and things like this. That's what you want to characterize, for example. But yes, it will have an emission. And if you have something which is rather hot, typically the warmer, the more the peak of emission of this body will be in the visible range or even the UV and so on. So 2000 degrees Celsius, it's about 2.3 kilokelvin, 2300 Kelvin. So basically the peak of emission will be closer, I would say just like this, 1000, maybe 1000 nanometers. So then what you will observe with the FX50 will be more the tail of the emission of your object. So you will have the possibility to measure it, you have the possibility to see it, then you just have to think what is the emission of the gas, and then you can monitor what is the gas, which is actually at which temperature and so on. So yes, 2000 degrees is a possibility. What conveyor belt speed can be realized? It depends on the size of the samples you want to sort. So basically, if you have large samples, let's say this paper like this, to measure it, to sort it, you don't need to have lines everywhere to keep the aspect ratio. What you could do, you can take, for example, 3 lines, that's enough to identify it. So, if you have a large object, you can have a belt which is going faster. If you have a small object, you need to have a belt which is going slower, keeping in mind you are using the camera at the maximum speed. So you have to think about that. What is the frame rate that you can use with this camera? And remember that full frame, it's about 380 frames per second. Full frame, I mean full spectral range. But if you crop it, then the camera can get faster. So depending on the maximum frame rate you can use and the size of the object you want to detect, then the belt can be slower or faster. And actually, it comes to another question which was asked in the chatter about the minimum size of the object that can be detected. It's again, I'm used to say it's about 3 times the pixel size. So you take the size of your conveyor belt, you divide by the amount of pixel, which is here 640, and you consider about 3 pixels to give you the minimum size of the objects that can be sorted. You can think in the width of the field of view, but also 3 pixels in this direction if you consider the speed of the belt. Okay, does the instrument need preventive maintenance like gathering, or if so, how often should it be done? So this camera, if you use it, it has a Stirling pump. That's the fact that it has a cooling system which is based on the Stirling pump, and we warranty for a certain time of hours. So if you want to use it online, if you want to use it, on shift, which is like 7, 8 hours, 15 hours, after some time, after some years, this is true that the pump will be wearing and it will be relevant to change it before that it breaks down. That's the preventive maintenance. Another thing is that if you have the camera yourself in a laboratory and you don't use it very often, we recommend to use it at least once a year, so that actually the vacuum chamber, the cooling and things like this are still run from time to time. So just don't leave it there for 2 years, 3 years without touching the camera. We recommend once, twice a year still to run the camera so that it's still operational. Do you have any experience analyzing fermentation system with MWIR? No, I have to say fermentation system I haven't tried. Neither with any hyperspectral camera, so that neither included MWIR. This is not something I have experienced. Then the question is like, what do you want to measure? What are you interested in? Do you want to measure like some gases? Do you want to measure some rays of temperature? Yeah, so it's hard to say just like this, but just like this fermentation system, no, I do not know. how important it is to have standardized lighting in terms of sample analysis. Well, first of all, you are raising a point which is important, it is illumination. We are talking about the thermal infrared now, and this is the first webinar, if you consider the series we are having so far, which doesn't require to have halogen or like LEDs or things like this. So now we are talking about thermal illumination. And as you saw in the presentation, basically it looks like an electrical barbecue road. It's at about 650 degrees Celsius, it could be a little bit warmer as well. And this is the illumination you are using. So it's good, first of all, to have an illumination which is compatible with the spectral range. That's the first thing. The second thing is like when you process your data, you normalize your data. So basically, you get rid of the illumination influence. You want to really measure the reflectance of the emission, but here it was the reflectance of your sample. So this is normally free of the illumination. But okay, if you have an illumination which is not evenly spread over the full spectral range, you will have issue with the SNR at some wavelengths or these kind of things. But you need to have an illumination which is matching the spectral range. And here, this is the most important. Can the FX system differentiate between PA6 and PA6.6? And I will add even PA12. No, I have tried to sort different type of polyamide, 6, 6, 6, 12, and here, no. The camera was able to separate PA from the other polymers, but not PA and the subdivision of PA. So the camera could not do it. Can the FX50 also be used for airborne application? Well, theoretically, it could. But you have to consider how to use it. We haven't tested it ourselves at Specim for airborne application, meaning like the vibration you have in an airplane and things like this. So here, it is somehow at your own risk if you want to implement it. Also, like for the long-wave infrared that we are going to speak about, by the way, on the 22nd of February, here it's always good to have a black body mount which is going in front of the camera before or after each flight line. So that's something to keep the possibility to have radiance conversion of the data. And finally, this is a tricky spectral range. This is a tricky spectral range because you have a lot of atmospheric contribution to the signal, either absorption, either some kind of emission which is contributing to the signal, and at the lower end of the signal, basically you measure mostly the reflection from the sunlight compared to the emission of the sample. But when you go to the longer wavelengths of the spectral range, this is the opposite. The emission signal of the sample you measure is actually dominating the reflection. So you have to be able to separate, the emission from the reflection. So it makes things a bit more tricky. So yeah, so there are possibilities, but it's not straightforward. But then the device, as said, it's not certified or tested for airborne use, but if you want to use it for this, you are free to do it. What will be the smallest item you can measure? I answer this question. What are the power requirements of the FX50 for field application? This is exactly the same as it is for industrial application. I don't remember the power consumption. It was in the data sheet. I prefer not to say anything which will be not correct here. So check the data sheet, and here you have the power requirement.
It's shared in the files. You can download the data sheet.
Okay, so we heard that it says in the file you can download the data sheet. What thickness of sample can the FX50 penetrate? Well, first of all, the wavelength is longer, and the penetration depth depends on the wavelength you are using. So here, the longer the wavelength, the more you have the penetration depth. But it also depends on your material. You have some materials which are really opaque, you have some which are more transparent, so it depends on that as well. So I don't have a definite answer, but it's more than with the SWIR, with the VNIR and with the NIR, but still it's a surface measurement system. I mean, it's not like X-ray. You do not see through the things, but still the penetration depth is more. But again, it depends on your material. Did you ever think of distinguishing metals, aluminum versus copper versus steel, considering that the reflectivity of different metal is different in the spectral range, it will not only be the reflected light spectrum, but different intensity for different frequencies. Well, different intensities for different frequencies, it means that you have a spectrum. So that's what it means. But I have to say the FX50 is used in the metal industry to separate different type of contaminant you could have in the metal, but also to separate different type of oxides. But keep in mind that a metal doesn't really have, like, if it's not oxide, but the pure metal doesn't really have any like chemical, like molecular structure. It's only the atoms next to each other, so you have very little of actually like spectral information. But if you think about recycling industry, yes, a lot of people ask us if actually we have any spectral camera which could be used to separate those. And I must say here the best one would be the visible camera, the FX10, which is between 400 and 1000 nanometers, because typically metals, they have different colors. And the FX10 can measure accurately the colors of the different metals. So some research made by some of our customers was done for the separation of metal, but it was mostly with the FX10. With FX50, you can measure some other things, as I mentioned previously. You mentioned a cloudy day giving less signal in the field application. Why is this? Well, so because the sun has warmed the same target? No, because if you have a cloud, basically you have something between your light source and between your sample. So the cloud could be seen, you know, as a filter, as something which is attenuating some of the wavelengths. And a cloud, what it is mostly water. So if you have like a filter made of water between your light source and actually your sample, you can imagine that all the wavelengths that water is absorbing will not be able to penetrate. So for instance, if you have a cloudy weather, typically you are restricted between 400 and even like 800 nanometers, because after that, water absorbs a lot. And for the FX50, there was in one of the slides you could see you have the CO2, you have the water, you have different things, which is actually different gases who are having a lot of absorption for these wavelengths, and then it might be a problem. Can you measure through glass? It depends on the glass. It's again, you have some glass which are really transparent for the FX50 spectral range, and for instance, you have some based on germanium that will work really well. I think sapphire could be another option, but if you think about the lens we are using in our FX50, it needs to be based on a glass which is transparent for the spectral range. And you cannot use whatever glass. If you just use a glass like you have a windows, you see we have windows here. If you use just those ones, no, the FX50 cannot see through. Have you ever tested the spectral range in cultural heritage application? Yes. Yes, actually we did. And that's actually a really good spectral range for that because it has a longer penetration depth as a shortwave infrared. So actually you can see a little bit deeper in the painting. So you can see like the underlayer, but you can already see it with some other wavelength, but here you can do it as well. And you can separate as well different type of pigments because most of them, you know, in the old times, they were made with stones, like different type of minerals. So here again, the FX50 can bring some information to separate those different type of pigment. So yes, in cultural heritage, like painting, this camera has been used. How to detect 500-degree gas inside a steel pipe? Well, if you have a steel pipe, basically you have the gas which is in there. The steel pipe make it completely opaque to the hyperspectral camera. So here you have no chance to be able to see it. You need to have it like transparent in a way. So the steel pipe is not an option. You could be able to see the leaking. Maybe you're interested in that. But to see inside the steel pipe, that will not be able to work. So the first question was about the camera itself. Is the camera a cooled camera? Yes. The detector which is inside the FX50 is actually a MCT. It's based on MCT and it is Stirling cooled. So it is. This is the latest version of the camera. Even the previous one was also cooled. It was based on INSP. But the one we just released this month is MCT cooled. Can you apply this technology to food chemistry? That's interesting because we got this request actually like a few years ago to inspect cocoa beans, or we had it actually not a long time ago to inspect like fish fillet. And it could be used, but this is not the camera which is used the most for like food chemistry analysis? It depends what you want to look at it, what you want to look at, of course. If you're interested in moisture or fat content, I would rather go for FX17, meaning NIR between 900 and 1700 nanometers, or with the shortwave infrared, which is between 1000 and 2500 nanometers, because this is where you get actually like some nice spectral features. Moisture, as I say, so sugar content, salt can also be seen with those. But with the mid-wave infrared, you may get something, but maybe not the most suitable spectral range for this type of application. Can you provide example of detection accuracy of mineral containing carbonates versus sulfates? I cannot give like example of detection accuracy, but we have a partner who is really specialized in geological application, looking at drill cores. They have been trying our FX50. And they mentioned that yes, this spectral range could be really suitable to separate like at least the carbonate and some others, those which are mentioned like this in the presentation. Carbonate and sulfate, to the best of my memory and to my experience, I would say the shortwave infrared is also a good spectral range for that. The long-wave infrared. But the interesting part with the geological application is like the mid-wave infrared is a spectral range which hasn't been used extensively for geological application. So when we look at spectra of different type of mineral, we see a lot of spectral features. So we see there is a high potential, but little research has been done for this spectral range for this application. So here, this is still something that people should work on to get more and more, but there are interesting things to be done. Can you focus the camera? Yes, sir, you can do that. And actually with the FX50, we can provide 3 lenses with 3 different types of field of view. We have 24 degrees, 45 degrees, and 60 degrees. And yes, you can adjust the focus of the lens. And for all of the 3 lenses, the minimal working distance is actually 30 centimeters. So if you get closer than 30 centimeters, you cannot focus, but then it could be focused then until infinity. So minimum working distance, 30 centimeters, and then to infinity. Does your software background out the CO2 contribution you showed, or is that considered, oh, I got a new question, so it jumped, or is that considered as an unused bad band with this camera? Is it really considered as a bad band? It's like you have some application where the CO2 need to be monitored. So if you want to monitor like CO2 leaking, or if you want to check the spectral calibration of your camera, this is not a bad band. But if you want to work, for example, in black plastic or things like this, something else, then I agree with you, it is a band that you don't want to look at, all this spectral range, which is about 4,200 nanometers. So our software doesn't take it away automatically, but with Insight, our processing software, you can make multiple regions of interest. And for example, you can make one before the CO2 and another one after the CO2. So then you can remove on your own the CO2 contribution. So yes, it can be done with our software. Okay, so then how can I fit a curve according to Planck emission to it? By knowing the sample temperature, can I get rid of the temperature dependency of the spectra? Yes, that's actually a really good question, and it's interesting because we just wrote a technical note about that. How to extract, you have spectra, and how to extract the emissivity, and how to extract it to make it separated from the temperature. Because you are right, when you measure like samples in the thermal infrared, and what I say now applies as well for the long wave infrared. So basically you have a contribution of the temperature of your sample, and you already see it. And if you want to get rid of it, then you have to feed the Planck curves and so on. But now you have to think which wavelengths we are talking about. We are talking here about the wavelengths between 2.7 and 5.3 micrometers. So basically, you can start to have the emission, which is quite important when you have a sample which starts to be pretty hot. So when you have a sample which is pretty hot, then you are right, then you will have a mixture of the emission of your sample. It's like you need to get rid of that. I don't have a recipe how to do it. It's just that you take the spectra that you get from the camera, then you need to convert it into radians. And once you are into radians, you can fit a Planck curve to the top of the spectra that you are measuring in radians. And then from that, you can see the deviation from the theoretical perfect black body from actually what you get. And here you can see what is the emissivity. But again, you have to consider it depends on the temperature of your samples. If you have something which is really hot, actually this effect could be seen as well for shorter wavelengths, not what we call thermal infrared, but you could see it already for the shortwave infrared, for the FX17, and even for the visible. If you have something which is as hot as 7,000 Kelvin, for example, then, or 3,000, then you could see already this influence. And it raises another question, like when you are making measurements, your sample should not heat up too much because you know it will emit exactly at the same wavelength where it absorbs. So when you measure reflectance spectra, the spectral feature will actually vanish. Should you cool down your sample for better signal? Well, it's a little bit what I was explaining. So if you want to work like this with the FX50, I'm used to say that the sample should be at room temperature because for FX50 it doesn't affect so much, especially if you work in reflectance. If you work outside without illumination, then you have something which is interesting, is like under daylight, at the beginning of the wavelengths, actually the reflectance from the sun is dominating the emission of the signal, but at the end of the wavelengths, then you have the emission from the sample which is dominating actually the reflectance from the sun. So you have those things which are actually pretty tricky, that you need to separate the emission from the reflection. But that's how it is with this wavelength. That's why it's not used that much actually in remote sensing, and also due to the atmospheric absorption. So don't cool down your sample for this spectral and just use it as a normal temperature, like ambient temperature. I'm from Turkey. Heavy earthquake risk and earthquakes unsafe. More than familiar structure must do detection. Do you have info or example to concrete strength detection? I would say here we have seen shortwave infrared which has been used to detect different type of concrete, different type of building materials which has been used on houses, on buildings. So basically, with the shortwave infrared, you have the possibility to separate like which type of material, if you have had renovation, for example. And here, yes, we have seen this type of research, and maybe you could see as well, these kind of things. So if you had some renovation or no renovation, things like this. So we have seen this type of research. Can we use for food, packaging, and oil and energy application? Okay, so here we are talking about a lot of wavelengths. So if you are talking about food, I already mentioned before, like which wavelengths are better suited. Packaging, if you want to see like heat seal inspection, if you have some leaking or lack of glue or things like this, it's better to go for like wavelengths between 900 and 1700 nanometers. So here you have the possibility to see through the sealing and the the plastic cover. If it includes too much aluminum, if the aluminum is too thick, then you could not see through. Oil and energy application, it depends what you want to do. Oil and energy application, if you want to see some leaking, if you want to make some drill core inspections, here you need to be more accurate, but a bit more precise in your question. But for oil and energy application, yeah, well, it touches so many different aspects, so you could use many cameras for that. Can this be used for on the field for detecting edge pattern on stones for archaeology? This camera could be used on the field, and I think you saw actually in the presentation that this camera could be placed on a rotary scanner, and then you can visualize this, what you get from your samples. You need to have a black body, which is part of the scene, to be able to make the radiometric calibration to convert the raw data into radians. Here, you could do that. But is it really for archaeological application? Again, it depends what you want to see. If you want to see different type of material, maybe I will go more like for the shortwave infrared. If you want to see the collagen in the bones, then you could go for FX17 and the shortwave infrared. So it depends the application you want to do. And stones, yes, you were really pointing out for like on stones, for archaeological stones. It's more like geological oriented, like in a way of seeing the material. So again, shortwave infrared, mid-wave infrared, long-wave infrared, those are the camera you could play with. Hyperspectral imaging and data analytics for civil and structure inspection. Yes, so I answered this question already. what is the size of the scanning line and what is the trade-off between resolution versus distance. Okay, and then there was like 2 examples. The size of the scanning line. So if I recall well with this camera, yes, now I recall well. So basically, let's look at the camera is looking like with a triangle, like this, and then you have the pixel size. So basically, you take the field of view divided by the amount of pixels. And here with this camera, you have 640 spatial pixels. So this is the size of the pixels in this direction of the field of view. But then the width of the line, it is about 3 to 4 times the size that you have of the pixel in this direction. So in this direction, along the field of view, if you have 1 millimeter, the width, it's about, if I recall well, 3 to 4 millimeters. So this is the way it is with this camera. So, and then the trade-off, the further away you are, the more the pixels, they get bigger. So here you have to think what is the smallest object you want to detect, what is the measurement distance you can have, and I don't have like just an answer like this. So if you have a 1 meter field of view, or if you are located, let's say 1 meter away or 10 meter away, you can imagine that if you are 10 meter further away, it's 10 times more than 1 meter, so the pixel size will increase by 10. But I'm used to say that the smallest object you can detect, it's about 3 times the size of a pixel along the field of view. Are you affected by scattering? As much as in the NIR, how deep is sample do you measure? Yes, actually scattering here is important, and I will take an example, for example, for the black plastics. In the black plastic recycling industry, very often you can get like electrical appliances which are shredded, and then you have some really nicely shiny parts which are black. And if you have a diffuse geometry is what it means. So basically my head will be the camera, and my fist will be the illumination. And then you have the illumination like this, but if you have a sample which is super shiny, the signal here just reflected as a mirror, and you don't get anything from the camera. So here, yes, it has an impact. So actually you could think about 2 approaches. If you have super shiny samples, it may be better to use actually the camera in the specular geometry, meaning that illumination here, sample like this, and the camera here. So specular like in a mirror. And then here, if you have your sample which is diffuse or shiny, it doesn't really matter because you will still get the signal. If you want to have a diffuse geometry, then it's important to have diffuse samples. And here it has a strong effect. And as you say, it's the same as with the NIR. And how deep in the sample you measure, but it depends on your material. You have some samples, some materials which are actually more transparent than others to different wavelengths. So I don't have an answer just like this. But theoretically, and as a rule of thumb, the longer you go in the spectral range, the more you can see through, or you can see inside your sample. So it's deeper, but I cannot say how much. Rather than having camera rotating, can we use rotary stage to map smaller objects around? Yes, you can do that. For example, I have seen application where someone wanted to measure a drill core which was not cut by half. So basically you can put it on the rotary stage, the camera is fixed, and then you make the stage rotating like this, and then you can image your sample all around like this. I've seen this kind of geometry like to measure like this for drill cores. I have seen it as well like for like can inspections. Yeah, many industry actually, they prefer to rotate the samples than the camera. Is the data output you see in your software in radians? Does your software offer ways to get emissivity out of this? Is emissivity as useful as MWIR as in LWIR? Okay, let's take all those questions by one. Is the data output you see in your software in radians? You can see everything. So if you want to see the radians, you can, but you need to have a radians conversion. So for doing that, you need to have a radiometric calibration. And then by having the radiometric calibration, you can then convert the raw data, removing the dark, and then getting the radians. But now we are talking about a different wavelength than what we were used to speak about, and I will spend a little bit of time here. With the camera we have before in the previous session, which were between 400 and 2500 nanometers, basically the radiometric calibration was not affected by the temperature of the optics. Not that much. For the shortwave infrared, it starts a little bit, but it's not really dramatic. So here you could have a radiometric calibration file that you can use on the field without any problem when you are making measurement. And if the optics is at, I don't know, for example, 20 or 25 degrees, it's okay. Here it's a bit different because the optics, the front objective that you are having in front of the camera to define the field of view is not at 0 Kelvin, it cannot be. So it means that it has an emission. And the emission depends on its temperature. And when you are making a scan, a measurement outside, or even in an airplane for airborne application, so here, even if you have a small difference of 1 or 2 degrees in your front objective, the emission will be different, and then the radiometric calibration will be different. So here we cannot provide with a radiometric calibration file, but you need to have like a black body within the scene, or which can go in front of the camera, so that you can get, for every data acquisition, a radiometric, or how can I say, a black body related radiometric calibration file, and then you can do the conversion. And our software, unfortunately, doesn't have this. We have a routine which is based on MATLAB, which allow you then to convert the data into radians. Once you have that, that can be opened in our software. Does your software offer ways to get the emissivity out of this? No, our software inside doesn't offer this possibility. It offers only to get the reflectance, or then to look at the radiance when you process it and you have it with a MATLAB routine. But yeah, this is what we have. And is emissivity as useful in MWIR as it is in long-wave infrared? Yes, it is comparable. You could see it both ways, both spectral range quite similar in the way of processing the data. Can I recommend some literature about MWIR? No, I don't have anyone coming to my mind. I would say look at Google. Typically, it knows quite a lot. So, but no, I don't have any special book for that. But I have to say it's mostly experience as well. When you start to use this spectral range, you start to be acquainted with the pitfall or with the advantages, things you can do. So, yeah, that's what I could recommend. Okay, so thank you. Thank you very much to all of you who has been here for this evening for me session, maybe morning for some of you. I wish you a nice day. I wish you to go on. And remember, we are going to have the next session about the long-wave infrared, which is going to happen actually on the 22nd of February, so it's about in a month about. Thank you again, and bye-bye.